In this video, I'm going to start talking about nucleophilic substitution reactions. And so, if you remember from the previous video, that's where we have something like this, oftentimes a halogen, but not always, which is attached to our substrate. And then we have this nucleophile here. So this nucleophile, these electrons are going to come and attack that carbon, and these will come off of here. Well, I mean, this is the SN2 reaction that we will be talking about. But if we just look at this in general, if we want to look at it more generally, all we're doing is removing this halogen and adding this nucleophile. So that nucleophile there, this halogen is removed from it, so that's called the leaving group. And so what I was just showing there was actually what we're going to talk about today, which is the SN2 reactions, where SN2 stands for substitution, nucleophilic, and bimolecular. So substitution, nucleophilic, and bimolecular reactions. And so what I was showing above is what I'm doing here. So we have this nucleophile, and so in this case, our nucleophile is this hydroxide, and our leaving group is going to be this iodine. And so the lone pair on that electron, on the oxygen there, is going to come and attack that carbon. And so the electrons from the bond to the iodine there are going to go onto the iodine like that. And so we end up with a transition state that looks like this, where we have the hydroxide here partially bound to the carbon and the iodine still partially bound to the carbon. And so we end up with this transition state that has this trigonal bipyramidal geometry right here, where we see I've had these hydrogens sort of move down this way a bit, so that we end up with the trigonal bipyramidal geometry right there. But then the electrons are going to continue moving over to that iodine there, while these ones continue strengthening the bond to the carbon right there, so that we end up with this as the product, where we now have this alcohol group on here. And so this product is actually methanol right here. And then the leaving group is this iodide right here, which has now left that substrate. And so the reason this is called bimolecular is because the rate is actually dependent on both the substrate, which is this right here, and the nucleophile, which in this case was this hydroxide ion here. And so the rate is actually dependent on the concentrations of both of those. And so it's bimolecular because the rate is dependent on both of them rather than just one. As we'll see in the next video when I talk about SN1, that is unimolecular, and so it actually only depends on one molecule. But we'll get to that in the next video. But yeah, the point is this is dependent on both the concentrations of both of these, the nucleophile and the electrophile or substrate here. So this is the energy diagram here. So we have our nucleophile and our substrate, the transition state here, which is at this higher energy. And so we do have the activation energy, which is the difference between here and up here. So that is our activation energy there. Then we have the difference between the reactants and the products, which is about here, which is going to be our delta H for that. And so we do see that this is, well, at least for the for this hydroxide and this iodine, this is an exothermic reaction. All right, so in general, this is our general SN2 reactions here. So I mean, it's pretty much the same thing I had above, except I've just replaced the nucleophile or the hydroxide with a general nucleophile and the iodine with a general leaving group here. But the reaction is still the same. So we have the nucleophile here, which is going to have these electrons attack that carbon. The electrons are then going to move on to the leaving group there. We go through this transition state where it's sort of partially bound to both of them with that trigonal bipyramidal geometry there. And then we end up with our product. So the product now has whatever the nucleophile was bound to our carbon, and the leaving group has now left. And I guess if I wanted to make this even more general, I would have changed all these H's into R's here, because this could be anything. It doesn't have to just be on a methyl carbon there. But anyway, that's the sort of scheme for that. And so then the question then becomes, once we know what the actual mechanism is, what sort of things are going to affect this actual reaction? And so that's what we're going to go through for the rest of this video. So factors affecting the SN2 reactions. So we're going to look at the sort of basicity of the nucleophile. As we'll see, it's not necessarily the basicity, although it correlates very strongly with the basicity of it. And we'll that has to do with the charge and electronegativity of our nucleophile, and the fact that a base is always a stronger nucleophile than its conjugate acid. So it also has to do with the size of the nucleophile and the substituents on the nucleophile, but also the substituents on the substrate, as well as solvent properties and leaving group properties. And so we'll look at each of these one by one for the rest of this video. All right, so the basicity of the nucleophile. And so the reason I said this was a bit more complicated than just basicity being directly correlated with nucleophilicity, although there is a very strong correlation, is that when we talk about basicity, we're talking about thermodynamic effects. And so remember, the strength of like an acid or base, so if we're looking at a base, we're looking at the Kb, which is going to be the concentration of this plus the OH minus here over the concentration of the A minus here. So the concentration of our base here. And so we see that as this is an equilibrium thing. So remember, we're talking about the A minus plus H2O going to our HA plus OH minus. So this is about equilibrium here, where with nucleophilicity, and as we'll see while we go through this video, this is a lot more kinetic. In fact, the textbook I'm using says it's purely kinetic. I don't know if I believe that or I buy that. I think it's you could say it's mostly kinetic, but I think this kind of goes back to something I said in a previous video, where kinetics really is just sort of looking at a particular part of thermodynamics and from a certain point of view. So it all comes down to thermodynamics. But when we are talking about nucleophilicity, we are mostly going to be talking about the kinetics of this reaction, where basicity has to do with the thermodynamics of it. And so just keep that in mind when I talk about sort of the basicity of the nucleophile being a factor here. What we mean is the sort of kinetics of, I guess, the acid-base reaction going on here. But, you know, a nucleophile is always going to be acting as a Lewis base, and so the basicity does have to do with it. But one thing where the basicity comes into play is that the conjugate base is always going to be a stronger nucleophile than a conjugate acid. So here we have this methoxide here. Down here we have this this methanol down here, and so the transition state for the methoxide is going to be lower in activation energy than the transition state for the methanol. So the conjugate acid is going to have a higher activation energy than the methoxide for it. And so the reason for that is because up here we have this negative charge, and so it's the partial negative is sort of shared across this entire thing. Where over here we have this positive charge. In fact, well, this would be partial positive because it's only a partial bond, and this is the partial negative. And so having those two partial charges there is going to be less favorable than sort of sharing this negative charge through all of this. And so here, we can see that this is a stronger nucleophile, but it's also a stronger base, where over here, this acting as a base, so we can act as a base. We do have these lone pairs here that can act as a base, but it's going to be a weaker base, and it's also going to be a weaker nucleophile. And so, as I said, there is a strong correlation between the strength of a base and the strength of a nucleophile, but just keep in mind, like I said, that the basicity of something is a thermodynamic or equilibrium thing, where the nucleophilicity has to do with with the kinetic component here. But yeah, so again, just the conjugate base here is going to be a stronger nucleophile than the conjugate acid. All right, so negative charges increases nucleophilicity. And so if we have this hydroxide, that's going to be a better nucleophile than just the water. If we have this right here, this sulfur with this sulfide here with this charge here is going to be a stronger nucleophile than this hydrogen sulfide here. This nitrogen with the negative charge will be a stronger nucleophile than this ammonia here. But nucleophilicity does decrease with electronegativity. And that's because when you have more electronegative atom, they're going to hold on to their lone pair more strongly than something that is going to be less electronegative. And so we see that, something like this is going to be a weaker or a stronger nucleophile rather than this hydroxide, which is going to be stronger than this fluoride here. And so as the electronegativity increases, nucleophilicity decreases. And nucleophilicity will increase down the periodic table. And so the iodide is going to be a stronger nucleophile than the bromide, which is stronger than the chloride, which is stronger than the fluoride. So our selenium here, our selenium anion here is going to be stronger than the sulfur, which is stronger than the oxygen. Then this phosphorus right here is going to be stronger than our nitrogen there. And so the larger the atom, the better it's going to stabilize that transition state by sort of, and this gets into the polarizability, which I'll talk about here in a few minutes, where it can sort of hold that negative charge better because it's larger and can sort of spread that negative charge around, which helps to stabilize it. All right, so the size of the nucleophile, as I said, which we kind of saw up here with this, is going to make it a better nucleophile. So if we're looking at the fluoride here, so we have this hard or small valence shell on the fluoride, and so there's going to be less bonding right here in the transition state. So there's sort of less overlap with this back lobe of the sp3 hybrid orbital. So we have this fluoride that's going to be trying to bond with that. So we see there's less overlap here, whereas if we're looking at the iodide, that electron cloud is much more spread out, so there's a lot more overlap going on here in the transition state. And so the iodide is going to act better as a nucleophile than the fluoride because of its larger size, being able to sort of engage in more bonding in the transition state here. And so that's going to help that become a better nucleophile. All right, so let's look at some steric effects of nucleophilicity. And so here is actually where the sort of basicity correlating with a stronger nucleophile kind of falls apart. And that's where we get these steric effects, which is very much just a kinetic effect. And so if we have this tert butoxide, which we see is a stronger base, has a pKb of negative 2.54, is actually a weaker nucleophile, where the ethoxide, which is a weaker base because it has a pKb of negative 1.9, is actually a stronger nucleophile. That's because with the tert butoxide, we have these large substituents on here that are going to sort of hinder it, that are going to sort of block the oxygen here from actually running into the proper spot on our substrate. Whereas with the ethoxide, we have only this one large group on here, and so this is going to be less blocked from actually running into our substrate. So we have our substrate right here, which remember is going to have these R groups like this. So it has these R groups here. And so if we have these more bulky substituents on here, when this is trying to find its way to that carbon, these things are going to sort of run into these things. This is going to run into that. And so it's going to be hindered from letting this oxygen actually get to this carbon right here. Whereas on this one, so we have our R groups right here. So we have our R groups here. So this is going to try running into that. Well, this carbon here only has these hydrogens on it, so they're not going to be running into these R groups as much, and so it's going to be less hindered. So I wrote the Arrhenius equation up here, and so it's this A value here, this A factor right here, which is sometimes called the pre-exponential factor or the collision factor. And so this is actually going to be what's changing between these. And so this A factor right here is what's telling us about, the molecules having a sort of proper orientation and things like that when they actually run into each other. And so we're going to see that something for tert butoxide here is going to have a smaller A value, where this ethoxide is going to have a larger A value. And so that's actually going to help increase the rate constant for ethoxide compared to the tert butoxide. So yeah, that is the steric effects on nucleophilicity. We can also look at the steric effects on the substrate, and it's very much the same as with the nucleophile, where if we have only these smaller groups here, they're going to be less steric hindrance. So if we have our nucleophile here, so our nucleophile right here, if we have just these H groups, it's not going to sort of block the nucleophile from getting into there. Whereas if we go to this tertiary carbon, we have our nucleophile here. When it's trying to come at this carbon here, these bulkier R groups here are going to block it from actually accessing that carbon, and so it's going to slow that reaction down. And so again, it's going to be, so if we're looking at our Kr here, the Arrhenius equation, negative EA over RT, when we have the tertiary carbon, it's going to reduce this A value here, whereas if we have just this methyl group on here, is going to increase our A value here, which will increase the rate constant and therefore increase the rate of the reaction. And so again, these steric effects for both the nucleophile and the substrate are very much the same, where the greater the number or size of these substituents on our central carbon that's going to act as the electrophile, the more hindered it's going to be, and so it's going to slow the reaction down. So our primary carbons here on the substrate are going to be better than secondary, which are better than tertiary, and on the nucleophile, the more substituents, so this tertiary carbon right here with this oxygen on it is going to be more sterically hindered than just this primary carbon here with this oxygen on it. And so we can actually look at some relative rates of these. And so this is for the substituents here. And so this is sort of, don't take these numbers seriously. These are just supposed to be relative. And so if we sort of normalize it to this one right here, so we call this secondary carbon right here 1, we see that on a primary carbon it's going to be 50 times faster. Then if we do it on a methyl group here, so just this bromine on a methyl group, so this methyl bromide here, it's going to be greater than 1,000 times faster. Where we see if we go then down to a tertiary here, it's going to be 1,000 times slower here. And so then if we go to this this N-butyl here, it's actually going to be 20 times faster, but that's because it's on this primary here. But then we see if we go to the isobutyl, so we're now putting substituents on a carbon that's sort of one further away from this actual electrophilic carbon right here. We are still getting steric effects, and so this is only going to be 2 times faster here than our secondary. So the bromine is still on a primary carbon, but we are now increasing substituents on a carbon that's further away from it. And so we do see that it is going to be slowing it down a bit when we compare it to like this primary up here where we don't have any substituents on this carbon one away. So then if we add yet another substituent on that carbon one away, we see that we are actually slowing down compared to our secondary carbon. And that's because there is still going to be some steric hindrance. There's still going to be this bulky group that's sort of getting in the way of your nucleophile coming at the substrate. All right, so now if we go over here, we can look at the solvent effects on nucleophilicity. And so what we see is that if we have protic solvents, and so remember that's solvents where it's going to have a general form that's like this with an H, or it could even be like an amine group like that. But the point is it's going to have like an oxygen or nitrogen bound to these hydrogens here, and so that is what a protic solvent is. So these actually work well to dissolve negatively charged nucleophiles. So it's going to help dissolve the nucleophile. So smaller anions are solvated more strongly than larger anions. And so that reduces the nucleophilicity of these smaller anions. And so the reason for that is when we are solvating the nucleophile, we have our protic solvent molecules here coming and forming a complex with our nucleophile right here. And so when we want this nucleophile to actually try attacking that carbon there, we actually have to break the bonds. So we actually have to break this bond right here, this ion dipole bond right here. And so we have to break the bond and sort of remove this solvent right here before we can actually attack the substrate, or it has to do that at least during the transition state. So we could think of it as like a concerted reaction where if we still have a partial bond right there, we're still breaking that bond. And so we have to try to break that bond, which is going to require energy to break that bond. So remember, breaking bonds takes energy, and so if we are solvating that smaller anion more strongly, it's going to require more energy to break the bond. All right, so aprotic solvents can enhance the nucleophilicity of anions, and that's because even if we have a large anion, which it's in a protic solvent, it's still going to be solvated. So you still have to break these ion dipole bonds between your nucleophile and the solvent. And so if we have an aprotic solvent, you're not going to have as strong of these ion dipole bonds. So, here where it's like this hydrogen ion, this hydrogen bonded to an ion, where if you have an aprotic solvent, it's going to be less strong because you're not going to have that sort of hydrogen bond to the ion there. So yeah, there are no hydrogen bonds to be broken, and so requires less energy for breaking ion dipole bonds. But it also reduces the solubility of polar and ionic reagents, so there's kind of a trade-off there. With these protic solvents, you can dissolve your nucleophile better, but then it is going to be solvated more strongly. I mean, the reason that it dissolves better is because it is solvating more strongly. So if you change to the aprotic solvent, you are going to lose some of that solubility, even though you are increasing the nucleophilicity. So the polar aprotic solvents such as acetonitrile or dimethylformamide or acetone can help increase solubility. So we want to use aprotic solvents, and we want them to be polar. So we wouldn't want to use like a non-polar aprotic solvent, like a diethyl ether or something like that. We'd probably want to use acetonitrile or this DMF or the acetone. We can also use solvating reagents, so things like this 18 crown 6 with the solvated potassium, and so that can sort of drag anions into solution. So this is that 18 crown 6 with that solvated potassium there. And so we could think of, our nucleophile, which is going to be negatively charged, is going to be like this. And so it's going to be able to complex with this potassium here. And so then the 18 crown 6 itself is actually fairly non-polar, and so that can actually help pull these nucleophiles into these less polar solvents. But then over here I just show we have our acetonitrile, our DMF, and our acetone, which are those polar aprotic solvents that I discussed up there. All right, so yeah, this is just showing using this 18 crown 6 with this fluorine here. So the fluorine is going to be our nucleophile here, and so we're going to that's going to sort of bond into the 18 crown 6. So like if this nucleophile was just the F minus there, and so that will sort of help drag it into our aprotic polar solutions here, or even something maybe a little bit less polar than that. But anyway, we're doing the SN2 with the chloride here as our leaving group, and then putting this fluorine on here. So then we also want to look at the reactivity of the substrate. And so the reactivity of the substrate is going to be largely dependent on how well of a leaving group we have. And so a leaving group has to serve two purposes in our SN2 reactions. And so it has to polarize the carbon to leaving group bond, so making the carbon an electrophile. And it has to leave with a pair of electrons that once bonded to the electrophilic carbon atom. So what that means is that we need the leaving group to be electron withdrawing, so it has to polarize the atom. So it needs to be more electronegative than the atom. It has to be stable, so not a strong base once it's left. So, that's why the halogens are often used as leaving groups, because these halogens, like the chloride here, is perfectly happy, especially in like a polar, and especially a protic polar solvent, is very happy just being negatively charged like that. And so they are very weak bases, and so they work well as leaving groups. So the leaving group also has to be polarizable to help stabilize the transition state and reduce the activation energy. All right, so electron withdrawing. So like I said, if we have the halogen here, so we're going to have the electrons pulled towards the halogen. So same with an oxygen or nitrogen or sulfur here. So we want those to be electron withdrawing from it. Again, we want a stable, weak base after leaving. And so if we have this bromide here acting as our electrophile, so what we can do is put this in as the hydrobromic acid here. And so this is actually going to protonate our methanol. So we will grab that hydrogen there. The electrons will go onto the bromine here. So then this bromide here can actually then attack this carbon right there. And the electrons from this will go onto that oxygen right there because this has that positive charge. And so that will make it a stable leaving group because the leaving group is just a water which is a relatively weak base compared to if we just tried to have like the bromide here attack the carbon. And so I'll put the hydrogens more explicitly on this one. So if we just had this, now we're trying to form a negatively charged ion here. And so that's going to be a lot less likely to happen because then the product is going to be our Br2C CH3, and then we're going to have this hydroxide ion here. And so this is going to be a less stable leaving group because it's a stronger base than this water, which is a weaker base. And so putting in that acid like that can actually help increase the rate of the reaction. So we can actually look at this here where we have these conjugate bases here like the iodide, the bromide, the chloride, this sulfate here. So these act as excellent leaving groups because they're extremely weak bases. So these conjugate bases, which are our leaving groups, are going to be extremely weak bases, and so they act well as leaving groups. So we can see that their conjugate acids are going to be strong acids, so that's that inverse thing where a strong acid is going to have a weak conjugate base, where a weak acid is going to have a stronger conjugate base. All right, so we see this hydrofluoric acid here, so it's a kind of an exception because this F minus is typically a poor leaving group because it forms strong bonds to the carbon. So that goes back to that thing I was talking about earlier where the larger atoms are going to work better as leaving groups. So like the iodine is going to work better as a leaving group, as we can see up here, in fact. Then we get down here to these moderate leaving groups here. So we have these weaker acids like the carboxylic acid and this protonated amine. These are going to be moderate leaving groups. We get to the poor leaving groups here like this methoxy right here, or this then we get to the extremely poor leaving groups. So like an amine being a leaving group is going to be very poor because these negatively charged nitrogens are going to be extremely strong bases. But anyway, we can just see the trend here where the stronger acid, its conjugate base is going to be a better leaving group if the acid is stronger. So these are some common leaving groups here. So we have some common ionic leaving groups here. So again, these three halides, the sulfonate and the sulfate. So these have those resonance stabilization, which helps make them better leaving groups because we can sort of accommodate these negative charges on these oxygens better because of that resonance stabilization. And same with the phosphate. And in fact, the phosphate being a good leaving group is sort of what makes it good for like an energy currency in biochemistry, is that these phosphates as leaving groups, so phosphorylating things in biochemistry, helps to drive reactions. These are some common neutral leaving groups, and so when these are bound to them, are actually going to have positive charges. So, we have our carbon here, then has the leaving group, like the water here would actually be like this, so it would actually be positive. But these are sort of the leaving groups after they have left. So like water, alcohols, these amines like this, and so this again, like I said, when it's bound, would be positively charged because we'd have a bond going right there. So phosphides and sulfides. And so again, the polarizability is going to make these better leaving groups. So these large or soft ions are highly polarizable, so they can engage in more bonding at longer distances, and this makes them good leaving groups. And so remember, the polarizability has to do with how well they can accommodate this negative charge, because the negative charge is sort of a cloud of negative charge. And so if you sort of compactify that cloud like this, that cloud is sort of, you know, repelling itself. That sort of weird quantum mechanical thing where an electron can sort of repel itself because it's in multiple places at the same time. So that makes it less stable than if you can have this larger, right here, this larger cloud. And so the electron is sort of spread out, so it's not repelling itself as much. And so that goes to the polarizability that helps stabilize the transition state, where we can see here, so we have our nucleophile on the carbon here. And so with like this larger ion here, like this iodide, the charge is sort of more spread out in this larger cloud here. And so it helps stabilize this transition state, where when we have this smaller one here, the charge is sort of less spread out, is sort of more compactified towards this carbon here, and so it's sort of repelling itself and making this a higher energy transition state, so it's less stable. And so this polarizability helps to stabilize the transition state. And so one thing you may have noticed as I was going through this is the stereochemistry of the SN2, where we are sort of inverting this. So we see this hydroxide here is coming at that carbon, and so it bonds there. This bromide is going to leave. And so we actually inverted this right here. So we went from this S2-bromobutane to the R2-butanol. And so the nucleophile electrons insert into that back lobe of the carbon sp3 hybridized orbital. And so if we look at the hybridized orbital for this bond to the bromine here, so we have that lobe right there. Remember, with the sp3, we do have like a small lobe on the opposite end there. So our hybridized orbitals have that small back lobe there, which is what the electrons from our nucleophile are going to bond into. So they are inserted into that anti-bonding orbital that helps the leaving group detach. And so we have this backside attack that turns the tetrahedron of carbon inside out like an umbrella. So if this is sort of the handle on our umbrella, and this is, our umbrella up here, it's been turned inside out compared to up here, where this is our, where this is the, well, not the handle, I guess it'd be the top of the umbrella. And so our umbrella is sort of, like that. And so now it's been sort of turned inside out like that. So the umbrella has been sort of turned inside out like that. So the incoming nucleophile assumes the stereochemical position opposite that of the leaving group. And so this is called inversion of configuration. And so in an asymmetric carbon, this gives the opposite configuration on the carbon in what is known as the Walden inversion. And so that's what we see here, where we are going from the S to the R here in this inversion. And so we have this chiral carbon here. So we have a hydrogen and a methyl group, an ethyl group, and this bromine. And so it's an asymmetric carbon. So it's actually going to change the stereochemistry on it. So we can look at just another example here where we have this here where we have this asymmetric carbon right here. So this hydroxide is going to come down and attack that carbon. So it's going to bond there. We end up with this as our transition state. So this bromine is going to leave there. And so we get the inversion where here we had this bromine pointed down. Now we have this higher priority one pointing up like that. And so we go from the cis 1 bromo 3 methyl cyclopentane to the trans 3 methyl cyclopentanol here. So we have that inversion going on. All right, so this is just a table of some common nucleophiles here. So we have like the iodide and the hydroxide here, and like this this right here, which could be like a methoxy or ethoxy group. So like the conjugate base of an alcohol group there. The sulfides here, which can act as these nucleophiles. And so from these, we are forming things like the alkyl halide, the alcohol here from the hydroxide, the ether here from the like methoxide, ethoxide, and things like that. We're forming a thiol here when we are using this, or a thiol ether when we are using this. So on and so forth, like with the amine here. So these are just some common nucleophiles and common products that we see with these nucleophilic reactions here. So these are just some concrete examples of everything that we saw going on above. Then we have nucleophilicity here in some polar protic solvents, and so we can just see that like these are some strong nucleophiles right here. So like the hydroxide, the methoxy here, our iodide, this sulfide here. We get to our moderate nucleophiles like the bromide, this amine, this chloride, this acetate right here. Then we get to the weak ones like the fluoride, our water, our methanol right here. But anyway, those are just some common trends we see here. But that was everything I wanted to talk about in this video. So yeah, the takeaways here. So we have the nucleophilic substitution. We were talking about the SN2, which is substitution nucleophilic bimolecular. So it depends on the concentration of both of those. We wanted to look at the basicity. So again, the basicity can have strong correlations, but it's not a perfect one-to-one strong base being strong nucleophile, weak base being weak nucleophile. It's not one-to-one. And so a big part of that was because of these substituents on the nucleophile and substrate where we can get stronger bases, but because we have more of these substituents sort of blocking access to the electrophile, that's actually going to make it a weaker nucleophile. And so, again, more substituents on either the nucleophile or the substrate is going to weaken the reaction or slow the reaction. It's going to make it a weaker nucleophile or a worse substrate for the reaction when we start adding bulkier substituents on it. We looked at the size of the nucleophile where when we have, especially looking at like the halogens, the larger nucleophiles are going to be better nucleophiles because they can sort of accommodate that negative charge better, and because there's going to be more overlap in the transition state, and so it's going to be a stronger bond in the transition state. We also looked at the solvent properties here, and so we saw that the best solvents are probably going to be polar aprotic because we want to be able to dissolve our nucleophile, so like our negatively charged nucleophile, so we do need something polar, but we also don't want it protic because we don't want it to solvate our nucleophiles too much, because then we have to start breaking those solvation bonds, and so that's going to require more energy. Then we also looked at our leaving group properties, and so remember, we want our leaving group to be stable as after it's left, and so we want it to be able to accommodate charges better after it's left. And so larger atoms, so like iodine is going to be better than bromine, for instance, but also if it has resonance stabilization, so like our sulfates and phosphates can act as good leaving groups. And so yeah, we wanted those larger ones because we wanted it to be able to accommodate that charge like in the transition state better. But anyway, these are sort of the things that are going to affect the reactions, so affecting these SN2 reactions here. So the nucleophile, the properties of the nucleophile, the properties of the substrate, these properties of the solvent, and the leaving group properties on the substrate. But anyway, I don't want to ramble on too long. I hope you found this video helpful, and I will see you in the next one.